Hey everyone, and welcome back. Today we're diving deep into something really fascinating. It's all about the surprising connection between artificial intelligence and those super fundamental laws of physics. You probably saw those headlines about the 2024 Nobel Prize in Physics.
Yeah, going to John J. Hopfield and Geoffrey Hinton.
Exactly, for their work on artificial neural networks. Pretty cool stuff, right?
It's not every day you see such a fundamental link between two fields that seem, at first glance, so totally different.
So we're going to go beyond just the hype around AI
Yeah,
and really dig into those core physics concepts.
exactly. Get to the nitty-gritty. You see, Hopfield, with his background in physics, he approached the whole problem of understanding the brain from a completely different angle. Like, it wasn't just about mimicking the structure of the brain.
Right.
It was more about understanding the principles, the underlying principles that actually govern how it works.
So he wasn't just copying the brain structure. He was trying to, decipher its code in a way.
Precisely. In his 1982 paper, Hopfield made this brilliant analogy. He connected the way atomic spins, tiny magnets, align in magnetic materials to the behavior of those interconnected neurons.
Okay, hold on. Let's unpack this magnet analogy a bit. So we've got these tiny atomic magnets, and they can spin either up or down.
Right.
And just like magnets can influence each other's direction, neurons in a Hopfield network can influence each other's state, whether they're firing or not.
Exactly. And that's where physics comes in and gets really interesting. Hopfield introduced the concept of energy into his network.
Okay.
A specific pattern of neuron activation, kind of like a combination of those on and off neurons, represent the stored memory. And this pattern has a certain energy associated with it.
So it's like the network's this tiny energy-driven universe.
Yeah.
Storing information.
You got it. The network learns by adjusting the strengths of the connections between these artificial neurons. So those memory patterns correspond to low energy states. Imagine a ball rolling down a hill. It naturally wants to settle at the lowest point, right?
Gotcha. So retrieving a memory is like giving that ball a little nudge and watching it roll back down to that same spot, that low energy state.
A perfect analogy. What's fascinating is that this model isn't just theoretical. Hopfield showed his network could actually recall a complete memory, even from a partial or distorted input. It's like remembering a whole song just from hearing a few notes.
Wow, even with the limited computational power back then. Hopfield's model could already perform some pretty complex tasks like pattern recognition. It's amazing how he bridged that gap between physics and information processing.
Absolutely. And building on that foundation, Geoffrey Hinton, in his 1985 work, took this neural network concept and added something pretty revolutionary, a probabilistic approach, inspired by statistical mechanics.
Probabilistic approach. Statistical mechanics. You're going to have to break that down for me.
All right, imagine a room full of gas molecules. They're bouncing around chaotically, right? Instead of trying to track each individual molecule, statistical mechanics helps us understand the overall behavior of that entire system by using probabilities.
So instead of dealing with certainty, we're dealing with likelihoods.
Right. Exactly. Hinton realized that a neural network settling into that low energy state, remember we talked about with Hopfield's model, could be seen as a system reaching a state of thermal equilibrium, a concept straight out of statistical mechanics. He took this idea and ran with it, using something called the Boltzmann distribution to describe the probability of a network being in a particular state based on its energy.
So he's bringing the randomness
Yeah.
and probability of the physical world into the neural network.
Precisely. And this led to the creation of the Boltzmann machine, a neural network that learns by adjusting its connection strengths based on probabilities rather than strict deterministic rules.
Okay, that's a big shift. So instead of just giving a fixed answer, the network is actually considering different possibilities.
Right.
And assigning probabilities to them. It's like the network saying, well, I'm not 100% sure, but based on what I've learned, this is the most likely outcome.
Exactly. And this probabilistic nature of the Boltzmann machine opened up a whole new way of thinking about machine learning, leading to generative models, which are capable of creating new data based on the patterns they've learned.
It's incredible how Hinton took Hopfield's work and kind of infused it with this probabilistic lens inspired by statistical mechanics. It's like they've built a bridge between the predictable world of physics and the unpredictable nature of learning, intelligence.
Fascinating, isn't it? And this is just the beginning. We'll delve deeper into how these ideas evolved and explore how they actually revolutionized the field of AI in the next part of our deep dive. Welcome back to our deep dive.
I'm still kind of wrapping my head around this idea that, we can use these physics concepts like energy landscapes and probabilities to really understand how neural networks learn. Such a cool example of how these seemingly totally unrelated fields can just like come together and lead to some amazing advances.
Yeah, it really shows how interconnected knowledge can be. And as we go deeper, I think you'll see how this fusion of physics and AI is still driving so much innovation today.
Okay, so last time we were talking about Hopfield's work, how it connected neural networks to the physics of magnets, and how Hinton brought in statistical mechanics to introduce that idea of probabilistic learning.
Right, and these weren't just some abstract theoretical breakthroughs. They really laid the foundation for the whole deep learning revolution that's just transforming the world around us.
Deep learning, that's what everyone's talking about, right?
Yeah.
But how do we actually get from those early models like the Boltzmann machine to these massive multi-layered networks that power everything from image recognition to self-driving cars?
Well, it's a pretty fascinating journey building upon those fundamental principles. One of the big challenges in training these deep neural networks is finding the best set of connection strengths, those weights that allow the network to, you know, do its job accurately. It's kind of like navigating this vast, multidimensional landscape, trying to find the lowest point, the global minimum energy state.
Oh, I see. So it's like searching for the most stable configuration, like how the Hopfield network settles into those low-energy memory states.
Exactly, but with these deep networks, that search gets super complex. Traditional training methods can get stuck in what are called local minima, those deceptive little valleys that seem like the lowest point but aren't. It's like, getting trapped in a small dip on a mountainside when the real valley is miles away.
So how do you even avoid those traps? How do you actually find that true global minimum? That sounds like a computational nightmare.
And it was for quite a while. But once again, Hinton drew inspiration from physics. He came up with this brilliant strategy called pre-training, using something called stacked restricted Boltzmann machines, or RBMs for short.
RBMs. Okay, so we're back to Boltzmann and statistical mechanics again.
Right. Think of these RBMs as individual building blocks, and each one is trained to capture a certain aspect of the data structure. It's like having a team of detectives, each one focusing on a different clue.
Oh, I like that analogy. So each RBM is a specialist looking for a specific pattern or feature in the data. And then by stacking them together, you can get a much more complete understanding of the whole picture.
You got it. And the cool thing about this approach is that these RBMs can be trained really efficiently, layer by layer, using an algorithm Hinton developed called contrastive divergence. Each RBM learns its own set of weights, capturing increasingly abstract representations as you go up the layers.
So it's like building a pyramid, starting with a broad base of simple features and then gradually refining them into more complex concepts at the top.
Perfect analogy. And once these RBMs are pre-trained, you stack them together to form that deep neural network. Here's the key. This pre-training basically gives the network a head start. It guides it towards a more promising area in that giant energy landscape.
Ah, so instead of starting from scratch, the network inherits all the knowledge from those specialized RBMs, giving it a better shot at finding that true global minimum. It's like having an experienced guide leading you through a tricky mountain range.
I like that. And this breakthrough really paved the way for training much deeper and more powerful networks, which led to the explosion of deep learning applications we see today.
It's amazing, right? We started with simple magnets, then incorporated the randomness of statistical mechanics, and now we're building these sophisticated structures like pyramids with RBMs. It's such a testament to how powerful it can be to draw inspiration from different fields to solve complex problems.
Couldn't agree more. And as we move into the last part of our deep dive, we'll see how these ideas have not only revolutionized AI, but are also finding their way back into physics and other scientific disciplines, kind of closing the loop in this remarkable way.
Welcome back to the deep dive. It feels like we've been on this incredible journey tracing the evolution of neural networks from those early physics-inspired models to the powerful deep learning systems we see everywhere today.
It has been quite a journey. And in this final part, we're going to see how the story has come full circle. With AI now being used as this powerful tool to unlock new discoveries in physics and other scientific fields.
So we're going from using physics to inspire AI to using AI to actually advance physics.
Yeah.
That's kind of a cool twist.
It is. It really highlights the symbiotic relationship between the two fields. Let's start with an area where using neural networks might seem, well, pretty intuitive: particle physics. Imagine trying to sift through these massive amounts of data from particle collisions just to find the signature of some rare particle.
That sounds like looking for a needle in a haystack, especially with all that data those experiments generate.
Yeah, it's a huge task. But this is where neural networks really shine. They can be trained to recognize subtle patterns that separate the signal from all that background noise, making the searches much more efficient.
So it's like having an AI assistant that can tell physicists where to look,
Hmm.
saving them tons of time and effort.
Exactly. And this has already led to some major breakthroughs. Neural networks played a key role in the discovery of the Higgs boson, the particle that's responsible for giving other particles mass.
Wow, so AI systems aren't just helping us understand data. They're contributing to fundamental discoveries about the nature of reality itself.
Absolutely. And this trend is going way beyond particle physics. In astrophysics, neural networks are being used to analyze telescope data, helping us identify distant galaxies, study how stars evolve, even search for exoplanets, planets orbiting other stars.
It's like we're using AI to boost our senses, helping us see further into the cosmos and unlock its secrets.
And it doesn't stop there. In material science, neural networks are changing how we design and discover new materials. By training on huge data sets of material properties, these networks can predict the characteristics of new materials, which speeds up the development of everything from more efficient solar cells to lighter and stronger alloys.
So it's not just about observing the world anymore. We're actually using AI to shape and engineer the materials that will build the future.
Precisely. And maybe the most amazing application is in biology, specifically studying proteins, those workhorses of life. Understanding their complex 3D structures is super important for developing new drugs and therapies.
But imagine figuring out those structures is incredibly difficult, like solving a giant 3D puzzle.
It is a massive challenge. Traditional methods like X-ray crystallography, they're time-consuming and really expensive. But AI has stepped in to revolutionize this too. Deep learning algorithms like AlphaFold have really blown people away with their ability to predict protein structures with incredible accuracy, just based on their amino acid sequences.
That's amazing. So instead of years of lab work, we can now potentially use AI to unlock the secrets of protein structure much, much faster.
Exactly. And this has opened up tons of possibilities for things like drug discovery, personalized medicine, and just understanding how life itself works.
It's incredible how these ideas that came from combining physics and AI have come full circle, impacting not just our technology, but how we understand the universe and ourselves. Feels like we're at the beginning of a whole new era of scientific discovery.
It really is an exciting time. Who knows what other amazing breakthroughs are waiting for us as we keep exploring this amazing connection between the laws of physics and the incredible potential of artificial intelligence.
Well said. A huge thanks to you for taking us on this incredible journey through all this knowledge. And to our listeners, thanks for joining us on this deep dive. Keep exploring, keep asking questions, and keep pushing those boundaries. Until next time.